recording. And let's keep going from the suggested practice problems. We left off with the suggested practice problems. We left off here. Where did we leave off? We left off here, number 18. Number 18, I'm pretty sure. Yeah. So, I'll find that in the text. Did we do 18? Yeah, we did 18. So 19 is the next one. Is that the? Oh no, it's another one of these questions. Okay. So yeah, okay. So let's look at 19. See, it scrolls so slowly for some reason. Okay. Oh no. Okay. 19. And is that the whole thing? No, it's this one.
How'd you get the textbook in the PDF?
I just got I don't forget how I got it either. Someone sent it to me,
okay.
or something. I can send it to you. I can send you the
No, it's okay. I actually bought the textbook. So.
Yeah. Okay.
Just
Nope.
Yeah.
So here and here. Okay. Your grandmother enjoys creating pottery as a hobby. Well, maybe a little smaller, not that big. Creating pottery as a hobby. She uses a potter's wheel, which is a stone disc of radius r and a mass of m. In operation, the wheel rotates at that many revolutions per minute. Okay. While the wheel is spinning, your grandmother works clay at the center of the wheel with her hands in a pot-shaped object. Into a pot-shaped object with circular symmetry. When the correct shape is reached, she wants to stop the wheel in as short a time as interval as possible, so that she makes the shape of the pot, so that the shape of the pot is not further distorted by the rotation. She pushes continuously with a wet rag as hard as she can, radially inward on the edge of the wheel, and the wheel stops in 6 seconds. You would like to build a brake to stop the wheel in a shorter time interval. You must determine the coefficient of friction between the rag and the wheel in order to design a better system. You determine that the maximum pressing force your grandmother can sustain for 6 seconds is 70 newtons. Okay. Okay, well, that's part A. So, you must determine... But you must determine the coefficient of... I guess that's the question. That's the question. Yeah? Someone say something? No? Okay. So we're figuring out what the coefficient of kinetic friction is here. You determine that the maximum pressing force your grandmother can sustain for 6 seconds is that. So let's start with that. I guess the first coefficient of kinetic friction. Okay, so what do we know? Okay, we know the radius of the wheel. We know the radius of the wheel, which is very useful to know because that was the problem with the last one. So 0.5 meters. We know the mass of the wheel, which is 100 kilograms. Okay. And we know that the initial speed is 50 revolutions per minute. And pretty much you want to stop it. So delta t is 6 seconds. Delta t is 6 seconds, right? 6 seconds. By applying a force of 70 newtons. 70 newtons. Yeah. Force of 70 newtons radially inward. And we're trying to determine the coefficient. So you're putting a wet rag so you can radially inward to push the edge of the wheel to make it stop. So I guess the wheel is spinning like this. It's spinning, whatever, clockwise or counterclockwise. And you, I guess to stop it, she pushes you push on the side of the wheel inward. I assume that's what that means. Yeah, it makes sense to me. With a force of 70 newtons. Okay, and it takes.
Is it just me or is the audio out?
Oh, maybe audio out on the other stream or which stream? Which stream is it?
Okay, I'll refresh. Thanks.
And so I guess you couldn't hear me, so that makes sense why I didn't answer. So 70 newtons inward. We're determining it takes 6 seconds to stop with that force. Okay. So how is it slowing down? Let's see. There's this. Okay. So when you put a force like that, let me think for a second. When you put a force like that, there's a force. There's the reactive force coming back out, but that's not that important. But there's also the friction that's being caused, and the friction is, so if the thing is spinning this way, then the friction is pushing that way, I think, right? So that's the direction of the force of friction in this case. So because the motion is this way, right? I think that might be wrong by that, but let's see. So this is not applying any torque, but this is applying some torque. right, to the whole thing, right? So, okay, let's figure out, it goes from that to omega final equals 0. So let's find the angular acceleration, I think. I think that might make sense to be the next thing, right? So omega final equals 0. Because we have the initial delta t, we have the force being applied. Oh, we don't really have much else. Well, no, I guess we can figure this out. Yeah. Yeah, we have enough to figure it out. So the formula, I'll put my formula sheet back out here. Just so I can see it. Okay. So the formula that we're going to use for this is omega f equals omega I plus alpha t. We want the angular acceleration. We know everything here except for alpha. So I can say delta omega over t equals alpha, which is...
Wait, do we need that? They gave us 50 revolutions per minute.
Mm-hmm.
So can't we just make it into rad per second? And that's the initial angular velocity?
We're looking for angular acceleration, though, for the whole thing. Right?
Okay.
Right. That's what I'm looking for. Yeah, and which reminds me though that I do need to turn that into revolutions into radians per second. So first, let me do that. So omega I equals 50 revolutions per minute. So in 1 minute there's 60 seconds, and in 1 revolution there's 2 pi radians. Okay. So then that is going to be 50 pi over 30, and that's, wish I had better lighting here. Well, I mean, I can't have better lighting, but it's okay. 5.24. 5.24, it's the units are going to be, so the revolutions go away and the minutes go away. So it's just radians per second. Radians per second. Okay, so we know our omega I. Let's find our alpha. So it's going to be final minus initial. Well, initial is 0, so it's just final. 5.24 over delta t. We said was 6 seconds. Right? So 5 answer over 6. Oh, so I got 0.873 radians per second squared.
Wouldn't it be negative because the initial was thing 5.25 and final 0, so 0 minus 5.25.
Oh, you're right.
5.25?
You're right. Yeah, sorry, I had it backwards in my head. Yeah, so final is 0, initial is 5.25, so it's final minus initial, so it's the negative of this. You're right. Yeah. How does that make sense? Oh yeah, because you're slowing down. Never mind. That does make sense. So okay, we know that, and now let's take a look at what kind of torque needs to create that, right? So the sum of the torques, right? The sum of the torques is equal to the inertia times the angular acceleration. So we know this now, right? We know this. We also know that this is a disk shape, right? And again, just like the times we've done before, and the inertia for a disk shape is 1/2 mr squared. And we know both those values. We know m and r. So we actually also know the inertia, right? And so then we can figure out what the net torque is. And since the only thing causing a net torque, I assume so, but yeah, I guess it doesn't say anything else about it. It doesn't say much about anything else here. So we assume that's the only thing causing a net torque is caused by this. So from that, we can figure, it'll be very helpful, right? We'll figure out pretty much a lot about that force, right? Okay, and so net torque. Let's figure out what the net torque is. Okay, let's figure out what that is. And so since there's only one torque, I'll just call it torque of the friction, right? Torque from friction. This is 1/2 mr squared times alpha. So 1/2 m gave us in the question 100 kilograms. R gave us in the question 0.5 meters. 0.5 squared. Times alpha, which we just said was negative 0.873. Okay, so the torque from friction is going to be 50 times 0.5 squared times negative 0.873. So the torque from friction is going to be negative 10.9 Newton meters, I guess, right? That's the units for, yes, that's the units for that. Wait, is that the units for that? Yeah, I keep forgetting the units for torque. Is that right?
Yeah, it's Newton meters, but you don't put it as joule though. It's in Newton meters.
Yeah. I see, yeah. Okay. So now that we know that the torque caused by this, we can look at, yeah, okay. How the torque, let's think about this. Let's forget the torque for a second. Let's forget torque and let's just look at this force. Let's calculate from this end what the torque should be, right? So the torque caused by that force, by the force of friction, is equal to the distance from the axle, right? To the magnitude of the force, right? Times sine of the angle between those two things. Well, the distance from the axle is just the radius, okay? So it's just 0.5. The magnitude of that force, well, we don't know, but that's the force of friction, okay? And force of friction, and the angle between them, well, that's just sine of 90. It's a right angle that's made here, or right angle that's made here. That's what matters, right? So we know that the torque from the friction is just equal to sine of 90 is 1. So we can just say it's 0.5, or I'll just write it like this. I'll just write it as well, right? It's 0.5 times the force of friction, the magnitude of the force of friction. Well, let's use that. Let's use that now, right? So this, we also figured out that the torque from the force of friction is negative 10.9. So we can just say, since we also know that torque from friction equals 0.5 times the magnitude of the frictional force, right? We can just combine these, and we say negative 10.9 equals 0.5 times the magnitude of the frictional force, right? So multiply this by 2, so negative is going to be 21.8. 21.8 equals the magnitude of the frictional force. Okay, well we found the magnitude. Well, it's fine. I'll leave the vectors off. We know the magnitude of the frictional force, right? It's negative because it's, yeah. Why is it negative? Well, negative.
It's in the opposite direction.
Makes sense, but shouldn't this not end up being negative? It makes sense. It is going in the opposite direction, so it is like a negative thing, but this doesn't really make sense. The absolute value of something is, I don't think it's a problem. I think we can keep going, but
Wait, the net torque is 0 and the the net torque is negative and the frictional force is negative, so they canceled out for me.
Is it maybe because it's a sine negative 90 degree? Is that a possibility?
What was it? Sorry, can you say that again?
Is it possible for it to be sine negative 90 degrees, which gives like a negative 1?
Yeah, that makes sense too.
You're supposed to put sine because if not, because you put sine for the opposite 180.
Yeah. Okay. So you put
No,
so
probably
you measure it.
whatever.
I guess. Well, but how would you make a rule out of that? Yeah. So you could use the sign to make it negative, but then you'd be measuring. I guess you'd be measuring this angle.
What did you get for net torque?
Net torque, I got 10.9, negative 10.9.
Yeah, and TF, you wrote TF?
Mm-hmm.
What is that?
Torque from friction. Torque from friction.
Yeah,
Oh.
the torque from friction would be negative force friction R sine theta, right?
Force of friction R sine theta. Yeah.
Yeah, because the force of friction is giving negative torque.
Yeah, it is. But yeah. Sorry.
TF is negative.
Mhm.
So when you put it in, it cancels out.
This isn't negative though. Oh, but it should be negative. Okay, yeah, because
Yeah.
it should be negative. That's the problem. Yeah. So
It's moving it counterclockwise.
yeah.
Sorry,
So that's what I was thinking. I know I always say the wrong one too. So I think this is the angle we're supposed to measure, which would be 270, and sine of 270 is negative 1.
We're supposed to put negative here. If you
Right.
put negative here,
Yeah,
then
makes sense.
You're supposed to put negative here because it's already already that it's going counter clockwise.
Oh, okay. You just manually put a negative sign here. That's all it is. So you
Yeah.
don't do whatever. You
Yeah.
don't do whatever with the angles. Okay, sure. Okay, either one of those would do the same thing. But yeah. So let's. I think that makes more sense. Just look at it. Since the torque is acting in the negative, it's acting like this is clockwise, so it's acting in the opposite direction. Then just you manually put a negative sign there. Right. So since you manually put a negative sign here, this will be a negative sign. The negative signs will cancel. So there you go. That was the problem. Okay, and so since we know the force of friction now, well, the force of friction, well, I guess we got to do our sum of the forces in the x and y direction. So let's say this is the positive y direction, right? And this is the positive x direction. Positive x direction. So the sum of the forces in the y direction equals well, the point. Oh, hold on. What are we doing now? The point isn't moving. It's just the angular. Yeah, I think it's just the sum of the forces is 0 for both of them. The angular, like the torque, is what's changing. The angular acceleration is changing, but the actual acceleration of the point, like the linear acceleration, I'm pretty sure is 0 for both of these. So it'd be m.
You don't need Newton's law for this question, right?
Well, not really. Like I could just jump right here and say the force of friction equals
Mu.
yeah, mu. Well, it is mu Fn, right? But and then what's Fn?
The force applied.
But
'cause that's like the
you have to use Newton's second law to actually show that that's what
Oh.
Fn is, right? That's what I'm doing, right? So yeah, but that's the only thing. So it's going to be the sum of the forces in the y direction. Well, it's going to be, right, so I said before we have the reaction force, right? That's Fn, right? So we're going to have F applied minus Fn equals 0. So F applied equals Fn. And there we go. That's all we need. I mean, we technically should do the other direction too, but I think people are pretty comfortable enough going like this, just saying, well, the force of friction is mu times the normal force. Now I know the normal force is actually just the applied force, so I can just put that in here. I know the force of friction is 20. Well, I'll do it with variables first, and then we'll go there after. So the force of friction equals mu times Fa, right? So 21.8 equals mu times the applied force, which is 70. Okay, and so mu should be 21.8 over 70. And I got 0.311. So there you go. That was a lot in that question. There was a lot. Happy we could do it, but there's a lot to deal with. So I'll do. Let me do B, and then maybe I'll do a recap of what we did after. So what if your grandmother instead chooses to? Unless anyone has any questions, they can of course ask. Your grandmother instead chooses to press down on the upper surface of the wheel at a distance r that from the axis of rotation. What is the force needed to stop the wheel in 6 seconds? Assume that the coefficient of kinetic friction between the rag and metal remains the same as before. Okay, so, well, now we have, what was R? 3 meters. Okay, 0.3 meters, I mean. So now we have a similar thing happening. It's just that instead of the force being here, the force is being applied downward at this point, right? And so now it's a similar thing though. So the force of friction is acting opposite to the motion. So like that, I guess you'd say like that. So it's a very similar thing that's happening. In fact, most of this will be the same. So we're asking, what is the force needed, pretty much. We know the coefficient of kinetic friction. R is the impulse. So we got to figure out pretty much what's the torque done by this, right? You got to figure. Well, let me map it out a little bit better. So me make sure I have that right. If your grandmother said choose to press down on the upper surface of the wheel at a distance of 0.3 meters. You know what? I'll draw a new picture. How about this? Yeah, I'll draw a new picture. Let's just take it from the beginning. Because I think it might be much more confusing if I do that. Can I crop the picture? No, I can't. Well, it's fine. Just ignore the beginning part. So, again, we know that... I gotta move this back here. Come on. Okay, we know that the mass of the wheel is 100 kilograms. We know that'll be part of the question. I'll write it again just here so we don't think it's part of something else. 0.311. Okay, we know delta t equals 6 seconds. Okay, we know that r in this case is 0.3 meters. Okay, that's the distance that they're applying the torque. Right, so not the radius of the actual thing, but the radius of the of where they're applying the torque. We also know that the angular acceleration, since we calculated it last time, it'll be the same. I'm pretty sure. Yeah, because it's going from the same speed to the lower in the same amount of time. Yeah. So negative 0.873. Negative 0.873 radians per second. Okay. And then we're looking for the force applied. That's pretty much what we're looking for, right? That's our target. Target. So one way to relate the force applied, so again, I'll draw a circle here. Now we have this, right? There's the wheel. It's spinning this way. Let's say the wheel is actually bigger, but this is the radius of like where they're applying the force, and the force is being applied down into it. Okay, so I don't know how to show that, but being down, maybe I'll show it like that. It's being applied down onto the surface there. So we're looking for that applied force. What is the torque done by that? So the torque done by that applied force. Oh no. There's no torque done by that applied force, but the torque done by the friction caused by that force. Well, that's still going out like this, right? And why would that be? Oh, because because R is 0. No, there's not 0 there. Hold on. Why would that be torque of 0? Why would this force do a torque of 0? The torque done by that is the distance from the axle, the applied force, and then the angle. Something's wrong with the angle. But what's wrong with the angle? It's at 90 degrees. So wouldn't that cause torque? Yeah, why would this... Anyone have any idea why FA... It shouldn't cause any torque, but why would FA not cause torque? Where in this equation? So, because TA would be the distance from the axle times the magnitude of the force times sine of theta, the angle between this and that. That's 90, so it looks like it should create torque. Maybe it does.
Think about it. Maybe. Oh yeah, maybe. No, I don't know.
It doesn't seem like it should. I don't think it does at all. But why not? It looks like it should in this equation. Can't draw an
It's
8.
directly down, so it doesn't make sense.
Yeah, it doesn't make sense that it would cause any torque. But again, where in this equation does that come in? Because if I just plug it in, R would be this radius, okay. This would be whatever. Well, that's what we're looking for. That's what we're searching, right? Sine of theta. Sine of theta would just be 90, wouldn't it? The angle between this vector and going down is just 90. Oops. Okay. Well, yeah. Why does it not? It really shouldn't. It doesn't make sense that it would. The friction is what's causing torque. Maybe because it's not like rotating in the same plane, like it's not acting in the same plane as the wheel, like the rotation, because it's acting like perpendicular to that plane. But isn't that what? I don't know. So let's say FA.
Wait.
Yeah?
Sorry, why are we assuming that there's not going to be any torque?
Because they're just...
The friction's caused by the applied force, right? So don't we just replace that, the It's like literally the same equation except for 0.3 instead of 0, 0.5 or whatever we had earlier. Solve for. Oh wait, we don't know. Never mind. Yeah, okay.
We don't know that, right? Yeah. So the only thing that's tripping me up here is just that I can't tell why FA doesn't do any torque. It doesn't. That's the problem, right? Yeah, but it isn't really important because I know. I mean, it is important, but I know it isn't producing any torque. So we can just carry on with the question, pretending like it doesn't. But if you just plug it in, it would produce some sort of torque. So that's why I'm confused. But I know it doesn't. Because it's if you just think about how it, like if you have a thing spinning and you push down on it, you're not doing torque. The friction from your finger pushing down on it, that's what's producing torque, right? But that actual action isn't like pushing down isn't slowing it down. It's the friction on your finger that's slowing it down. As opposed to like if I literally just like tried to push with my finger on the wheel spinning that way, that's producing torque because you're literally like slowing it down. You'll feel the pressure in your finger, like it's pushing back against you, right? But pushing down on it, you would just feel the how rough it is on your finger. That's what's slowing it down, not the actual like pushing against your finger. If you're imagining like something spinning, right? So I know that this must be 0. I know it must be 0, but it doesn't seem like it should be. Anyways, let's whatever. Okay, so let's do just a little bit. I think so. The force of friction, right? The force of friction is going to be mu times the normal force, right? And again, just by looking at it, we don't really have to do the whole second law thing. Maybe for the part marks one, they would want to see the whole second law thing, but we can see by this that Fn is just going to be negative Fa, really, but since we're talking about magnitudes, it's fine. It's just going to be Fa, right? Because what else is pushing against? There's no other forces here. So the normal force is going to push back up, right, against the applied force with the same magnitude, and then that's going to be the normal force that we want here for friction, right? So now we have a new equation, Ff, force of friction, equals, well, I should put magnitude bars around this, mu times magnitude of Fn, or Fa, sorry. Okay, well, let's find another expression for Ff. Well, I can just do the torque because of friction is going to be equal to its distance from the axle times the force of friction. Ooh, look, good, that's what we want. We want two things like that. And sine of the angle between them, which is 90 in this case, right? So, well, what do we know here? We know R. This is one of our unknowns. This is one of our unknowns, so it's okay. It's okay that we don't know it. We know this. We don't know the torque from friction, but there is a way for us to find that still, because the net torque is equal to the impulse. I think impulse. The inertia times the angular acceleration, and the inertia is 1/2 mr squared, and the angular acceleration is the angular acceleration. We know all those things. We know r, we know m, and we know the angular acceleration, right? So we can say 1/2. This was 100 kilograms. It should be 100 kilograms.
Last. We can just use that.
Oh, we did it before. You're right. We did it before, didn't we? Yeah. So we can actually just do it. Take it from here. I did the same thing here. It's the same torque because it's the same. Why is it the same torque?
Same
Oh, it's a
table.
different. It's a different R. Different R value. R is different. Here it was 0.5. Now it's 0.3.
Oh, yeah.
So may as well just do it from the beginning again. So
Yeah,
this is
that's
0.3 squared times negative, and the angular acceleration was negative 0.83. Oh, what was it? 873. Okay, so let's plug that all in. So it's going to be 50 times 0.3 squared times negative 0.873. So I got my net torque. Yeah, my net torque is negative 3.92. Well, do those 923 Newton meters, right? And since the torque is acting in the negative direction, right? Since the torque is acting in the negative direction, I don't know where to find that. Oh, here. Torque is acting in the negative direction. We put a negative sign in front of that, make it positive. Okay? So, oh, and also the net torque, the only torque that's there is the torque from friction, right? The torque from friction. Oh, you know what? To make that a little more clear, the torque from friction is in the negative direction. The torque from friction is in the negative direction. The torque from friction is in the negative direction. So finally, the torque from friction is just 3.93 Newton meters. Okay, well, so now we know this equation, right? So what we can do is we're solving for FF, right? No, we're solving for FA. Sorry, we're solving for FA. I'm going to take this, plug that into there, and then just rearrange for FA, right? Because we know everything else. So I will, so FF is mu FA, so I'll just write that over here. So FF, magnitude of FF equals mu magnitude of FA. And then our second equation is the torque from friction is equal to the distance from the axle times the force of friction times sine of theta. So I will plug that into there. So it's going to be the torque from friction is equal to the distance from the axle times mu magnitude of FA sine theta. And I just rearrange for magnitude of FA now. Right, so the magnitude of FA is equal to the torque from friction divided by the coefficient of kinetic friction times sine theta, times, there's an r in there too, times the magnitude, the distance from the axle times sine theta. Torque from friction, we just said was 3.93 over mu, calculated in the last part of the question, was 0.311. Okay. R is the distance from the axle, so that's just going to be 0.3. Okay, and then sine of theta is sine of 90. Because 90-degree angle. Right. Okay, and so then our final answer for the magnitude of the applied force should be, so I'll just plug that in. So 3.93 over 0.311 times 0.3 times sine of 90 is 1. So that's it. So my applied force should be 42.12 newtons.
Okay. Question: why would they give the time when we haven't used it?
We used it in the first part to calculate the angular velocity. We did that. We used it there in part A, and then we used angular velocity in part B as well. So you kind of use it in both parts.
Oh, so the time is the same? The time didn't change for the questions, like A and B?
It says when the force is needed to stop the wheel in 6 seconds.
Oh, okay. I thought it changed.
Yeah. The only thing that changed is like how the force is being applied, right? So, but that's and it's essentially the same thing, really. Notice the pictures are pretty much the same. I think actually the same, well, kind of. So yeah, definitely a big question. I'm surprised I could do that easily, right? Not that easily, but like I'm surprised I could do that like without all of a sudden being stumped. So that was good.
For part B, what's the value for theta? 90.
90, yeah, 90, because the angle between the radial vector and the force is 90. Yeah. Sine of 90.
Okay.
Okay, so let me see.
Can you summarize what you did in this question?
For part A and part B, I can do both. Just go from the start. Okay, so we have a pottery wheel that's spinning. To stop it, you're pushing your thumb or you're pushing a cloth, I guess, against the side edge of the wheel to stop it, right? We know the radius of the wheel is that, the mass of the wheel, the time it takes to stop, how hard you're pushing, the initial speed of it, and of course the final speed, since we're waiting for it to stop, is 0. So we know all those things. First thing I did was converted the initial speed to radians per second. And what I want to do is solve for alpha, the angular acceleration. Okay. Sorry, and also our goal is to find the, sorry, just to be clear, our goal is to find the coefficient of kinetic friction. So what I did is that I noticed that coefficient of kinetic friction is going to be related to the forces acting, right? Related to the forces acting there, right? Specifically the normal force, right? That's going to be the force of friction, right? And the force of friction is going to be related to the force of us pushing there, right? And so to figure out more information about that, I know I'm going to need angular acceleration. Right? I know I'm going to need angular acceleration and just acceleration in general. So I went right for that. Right, so to find angular acceleration, I just rearranged this. I knew everything here except alpha. So I found angular acceleration. And what I did is I said, okay, the sum of the torques is equal to the inertia times the angular acceleration. Well, sum of the torques, the only thing applying torque to this is the friction. Oops. The only thing applying torque to this is the friction. Right, this arrow there is not a force arrow. It's just me showing which way is the positive x direction, right? So so the only thing applying torque is that, right? This Fn is not applying any torque, and the applied force is not applying any torque, right? So the sum of the torques is just the torque from friction. It's equal to 1/2 mv squared. That's what the impulse, I always say impulse. That's what the inertia is, right? And we just calculated that. So we can figure out what the torque is from friction. Right? Figure out what the torque is from friction. And so... and wait, how did I do? Oh, yeah. Well, we can figure out what the torque is from friction. Torque from friction is equal to that. Okay? So kind of ignore past this. Hold on. Here is where I stop and I do something else for a second. So this is where I go back up to here. And I say, okay, well, the torque from friction, right, is going to be equal to R, right, the magnitude of the distance, times the force of friction, right, times the angle between them. Right, actually, I'll take those negatives off because I have a better way of showing that. Okay, so I can see now that the torque from friction is going to be equal to 0.5 because sine of 90 is 1. So it's just 0.5 times the force of friction. Right? And so what I do is I just plug that in here. But notice the signs are a little wonky. So what's happening is that I actually missed some negative signs here. So the sum of the torques, the force of friction is going in the negative torque direction, opposite. It's going clockwise. So there should be actually negative signs in front of all this. Right? So then when I put this new value in here, why is it negative?
Yeah.
Because this is the positive angular direction, but the torque is going that way. Notice because the force of friction is, right? So it's a negative torque. Right? So then here I end up with that negative 10. So I said over here that the torque, actually it's here that I stopped. Sorry, wrong place to put the line. So I said over here, negative torque from friction equals negative 10.9 Newton meters. That's what I calculated from this whole thing here. Then up there, I calculated the torque from friction is 0.5 times the force from friction. And so it would be, well, I just said that, right? I just said that. So then when I put it into here, it would be negative. So I kind of flipped the signs here for no reason. I flipped the sides that it was on. But right, so this got put into there, so it's negative now, and negative 10.9. This should really be the other way around to avoid confusion, but hopefully that makes sense. And then I just solved for the force of friction, right? So the magnitude of the force of friction was 21.8 newtons. I know the force of friction is equal to the coefficient of kinetic friction times the normal force, right? Well, what's the normal force? Looking at the picture, you can see that the reaction force of this, so that's why I started doing y direction, x direction, might be overcomplicating it like that, but you can also just kind of look at the picture and say, well, I'm applying a force, there's going to be a normal force pushing back on me, it's going to be equal and opposite. So but I also showed that here with the second law, right? So the sum of the force in the y direction is 0. So the applied force, negative normal force, they're equal. So notice I just changed that to applied. We know the applied force. I know everything here except coefficient of kinetic friction. And so then I can just rearrange for the coefficient of kinetic friction, which is 0.311. Okay, that was part A. Big already, big question. Part B was saying, okay, sure, you know the coefficient of kinetic friction. You know the angular acceleration. What if I say, well, I'm gonna have the spinning wheel, and I'm just gonna I'm not gonna put to stop it by putting the wet cloth across the side of it. I'm gonna press down on it, right? So how hard do I have to push for it to stop again in 6 seconds, right? Assuming now you know the coefficient of kinetic friction. We know that now, right? So how hard do you have to push for that to be true? So this was a little bit more of a side note of something that didn't make sense. So I'll put, well, I shouldn't really box it because that makes it seem important. But, well, actually, I'll say this. I'll box it and say, not important. It should be there, though, because this is something confusing. I don't know. Well, I guess it doesn't have to be there. But you know what? Actually, I'll just erase it because it isn't important and probably just confusing. So we know now that we have a new wheel, right? It looks like it's still on the edge, although because I drew this, like the wheel is actually bigger, but that radius is just the radius that where you're applying the torque, like where you're pushing down, right? So imagine like the wheel stops right there. So we're still technically on the corner of it, right? And so, well, I should draw it like that, right? So that's the radius, right? So we know now what we're looking for is the applied force, right? We're looking for how hard you have to push to stop in the same amount of time. Well, we know that the force of friction is the only thing applying any torque there, the only thing changing the angular velocity. So let's start working with that. The force of friction is equal to mu times Fn. Looking at the picture again, and you can use your second law to prove this, is that Fn is equal to Fa, the applied force. So we can rearrange this equation into that. Okay. Now we have an equation with Fa in it. That's what we're looking for. Do I know the rest of the stuff? I know this, right? I know this mu. We calculated the last part. I don't know Ff. I don't know the magnitude of the force of friction. So I got to start working on that. Let's try to figure that out. Well, looking at the force of friction, we know we can calculate the torque done by the force of friction is equal to the distance from the axle times the force of friction times sine theta. Okay. And I stopped that for a second. I don't do that just yet because what I say is that, well, okay, I know this, I know this, I don't know this, I'm looking for that. I also don't know this, but I can actually solve for that. I can solve for the torque done by friction, right? The torque done by friction, we can look at the sum of the torques. Well, the sum of the torques is equal to the inertia times the angular acceleration. So what's all the torques? The only torque that's applying to this is the torque done by the force of friction. And it's going in the negative direction again, right? Negative direction. So negative torque done by friction is equal to 1/2 mr squared, that's the inertia, times the angular acceleration. I just plug all that in, and I get the torque done by friction is 9.39 Newton meters. Why is that? Yeah, okay, it worked out, so it's okay. Yeah, but is 9.39 Newton meters, right? And so, well, I can plug that in here now. The torque done by friction, I know that. So I can combine these two equations. That's what I do next. I take that first equation, this equation, right? Rewrite it here. Take that second equation from here, this one. And I combine them. I put the Fs into there so that I have Fa. And now I know everything in here. I just rearrange for Fa of 42.12 newtons. Okay.
The angle between FA and R is always 90?
Not necessarily always, but if it's like a circle and you're going out of it, yeah, and it would be, yeah.
Okay. Thanks.
No problem. Okay, let's move on. So next question is, that was 19, so next one is 40, part A only. And that's the last question from rotation of a rigid object. Oh boy. This is chapter 10. Now we're going to 40, part A only. Is this the right spot? I think I'm in the right spot. Angular momentum 40. Yeah, it looks right. We're in chapter 10. Chapter 10, yeah, okay. So boy, what are we looking at here? Okay, so number 40, we're just doing part A. Is the answer for part A here? Yeah. So the hour hand and the minute hand of Big Ben, the Elizabeth Tower clock in London, are that many lengths long and have that many those masses respectively. Oh, there's a picture. I know it's not that important to have the picture, but still, you can use it. 10.27. It's way back here. Oh, it's just a picture of the Big Ben. It's not actually like there's no information on there, so I'll just leave it. Yeah, I think we know what the Big Ben looks like. So, determine the total torque due to the weight of these hands about the axis of rotation when the time reads that. Oh boy. Okay. So, let's give it a try. So the hour hand. Okay, we have a clock. Okay. The hour hand I'll draw in a certain color. So the hour hand I'll draw in green. And let's start with the first time. So the first time is 3 o'clock. Okay, so the hour will be at 3. And the minute hand will be up. Okay. So we're trying to determine the amount of torque done about the axis when the time reads when the times are these times. So, well, the only thing doing torque at this time is this one, right? Because this one, the torque done by it, it's a, the force that's being applied by this is the force of gravity, which is going straight down, right? So sine of 180 is going to be 0, right? But the force of gravity is acting here, right? The force of gravity is acting here. I guess we treat it like, no, we treat it like the center of mass. So we treat it like it's acting there. That's true. Okay, this is kind of a center of mass problem too. So we say it's acting at the center of mass. I guess we assume it's at the center because we assume it's uniform and all that, right? So now we just say, okay, well, the torque done by A, is equal to its distance from the axis, from the axle, times the magnitude of the force applied by A times sine of theta. Okay, well, what's R? R is going to be 1/2 of that length. Now let's get the lengths here. So I'll draw them like this. So that green one is, so the hour hand, the hour and minute. So the hour is 2.7 meters and weighs 60 kilograms. The minute hand is 4.5, I'll draw it in black, is 4.5 meters and where it weighs 100 kilograms. So the distance from the axle is going to be 1/2 its length, right? Because the center of gravity is at halfway there, right? So it's going to be 2.7 over 2. The applied force is going to be mg, right? It's going to be mg, just going straight down, right? And sine of theta, well, it's going to be, I guess we can just say sine. I'll go right away and say sine of 90. Okay, and so we can just do this. It's going to be 2.7 over 2 times the mass is 60, right, times 9.81. And let's just say this is positive, whatever. Doesn't really matter. There. So, because the torque done will be the same. So there you go. So this is going to be 2.7 over 2 just times 60 times 9.81. So the torque done by this guy is 794.6 Newton meters. Yeah, there we go. And that's the answer for that one.
I have a question. So, like, why is the magnitude of R 2.7 divided by 2?
Because we say that the force that's being applied to this object happens at the center of mass, right? It happens at the center of mass. That's how like we can say that. That's the point of the center of mass and center of gravity. Well, center of gravity more precisely. And so we know that that's going to be halfway through. Well, it doesn't actually tell us anything about it, but it won't be all the way over here. Definitely the center of mass won't be all the way there. It won't be all the way over here. It's going to be somewhere in the middle. And that depends on like oh no, actually here you go. You may model the hands as long, thin, uniform rods. So it's uniform. So it's equal density throughout the whole thing. So it'll just be in the middle. The center of gravity will be in the middle. And so you treat it like the force is acting at the center of gravity. which is halfway down the rod. Right. Maybe could someone... Oh, here's the answers. Answers to... I got negative. Why did I get negative? Oh, because it's going that way? Okay, sure. I guess so. So the sign of... How would the negative come out of here, though?
Maybe it's because you made 9.81 positive.
I guess so. I guess it's because I said this was positive. So I guess let's just say that's...
Oh, maybe. Oh, okay. Maybe because it's gravity, or because it's negative.
I mean, I did a little bit of like hand waving here to say, well, FA is mg. So there's probably it's actually at negative mg, and that's the difference. So negative. No, that doesn't make sense. That doesn't make sense though. Actually, torque should be negative because it's going you see it's gonna pull the hand this way, which is clockwise, which is negative torque. Negative torque is clockwise. Hold on, this doesn't actually make sense. What I said there.
I think torque is just one of those things that you have to put in the negative sign.
It should come out somehow, but I think it's okay. Like too, if you just think about
Isn't
it.
it because counterclockwise, I think, is positive? That's what my professor said. Counterclockwise is always negative. So it just has to be negative.
Yeah, like this goes counterclockwise, so it is negative. It definitely will come out of the math somehow if you do everything perfectly. But if at the end, I mean, I did the math, the end number's right. It's just that I missed the negative. I'm pretty sure it's because of this step here where I just said FA is mg. I'm pretty sure there's some negative sign in there, but it doesn't really make sense to say that actually. So I don't know. But yeah, or maybe in the angle, although that doesn't make sense either. But anyways, we know the torque has to be negative because it's going in the counterclockwise direction. So that's the answer. Okay, so then for number 2. Should I do all of these, or should I just do some of them? Or maybe I'll do 2 of them or something. I don't know. Up to whatever people want. Well, actually, number 3 I can do right away. Wait, number 3? Yeah, number 3 I can do right away. Right? Number 3 is it's at 6 o'clock. Yeah, 6 o'clock is going to look like that, obviously. Right? And
6 o'clock and this morning.
Right, yeah. So there's going to be no torque down by here. Torque. The net torque equals 0. Because the force is being applied down, so that's sine of 180. It's going to be 0. Here the force is being applied down. That's sine of 180. It's going to be 0. So 0. Okay. Then let's move on. So number 2. I didn't do number 2 yet. So number 2 is 5:15. So 5:15. I know my clocks is going to be, now we do have to get the exact angle right on everything here because that would be annoying, right? So which one was my minute? Which one was my hour? Okay, so 15, which one was my minute? Red. So 15, I don't know, I guess they probably want us to be exactly precise. So 5 would be there, right? 5:15. Yeah, we can do it. It's not actually that crazy to figure it out. So 5:15.
Each number is 30 degrees.
Each number is 30 degrees? Does that? Yeah.
Yeah.
So 360 divided by 12 is 30. So, put that like that. Yeah. So then there's plus 30 over 4, right? So that angle that it creates here. Well, I'll show the angle in just a second. But that's the setup of the hands here, right? This should be the. I'll make it a little shorter because the hour hand, but yeah.
So the 30 degrees thing, is that like something we have to know?
Well, I mean, you can calculate it pretty quickly, right? So we have a circle. It's split up into 12 parts, right?
Oh, never mind, I'm dumb.
Right? So you just take 360 divided by 12, and each of these sections will be 30 degrees.
It's like 37.5.
Including this is 37.5?
Yeah, including that is 37.
Okay. So what we need for this, again, are these things. I'll just copy them down here so that we have them. Oh no, it worked. I thought it wasn't going to work. So let's figure out the torque. So now both of them are doing torque, right? So both of them have a force acting down. Right? That force is Fg m, I guess, and this is FGG. And so, well, let's calculate each thing individually. So the torque done by FG red is the distance from the axle times the magnitude of the force of G red, right? Times sine of the angle between those two things. So that's just going to be half of that length, so 4.5 over 2, times FGR, well, that's just going to be mg, or I'll say mr g, like that, mass of red times gravity, times sine of, well, what's that angle? That angle is just 90 degrees. Okay, so it's just going to be 4.5 over 2 times 100 times 9.81. And again, it's going to be negative because it's going in the negative direction. So negative 4.5 over 2 times 100 times 9.81. So I got, so that's a negative sign in the front there, yeah. Negative 2,207.25 Newton meters. Is that going to be a big number? Yeah, it's going to be a big number. Okay, so that's the torque done by FGR, right? But let's figure out the torque done by FGG. That's going to be a little bit trickier. So the torque done by the force of gravity of the green one is equal to its distance from the axle times the force FGG, right? Times sine of the angle between those two things. Right? So what's the angle between the radial vector here, right, and the straight down, right? What's that angle there? So to figure that out, we're gonna need to know, well, okay, from here to here, if it was pointing straight down, right, that would be 180 degrees, but it's a little bit less than that. So how far is that pointing? Well, we have to figure out, okay, so it's pointing, so it's 12, 1, 2, 3, 4, 5, 4, 5 there. So this is 30, 60, 90, 120, 150, 150. So that's 150 degrees there. And I need to add this little chunk here because it's at a quarter of the way, right? Because we're quarter past the hour. So it's going to be quarter of the way to 6. So so it's going to be this angle, which is theta. Not theta. I just call it phi. Phi is going to be 150 plus 30 over 4, which someone said was...
you get 157.5.
157.5 degrees. There you go. Sounds good. Yeah. Okay, so we know that angle. And so now we can figure out that this angle in there, that's what theta is going to be, right? That's theta. So that's theta. Theta, I'll write it over here. Theta is 180 minus phi, right? 180, take back that amount that we didn't go, right? So 180 degrees minus 157.5 degrees. And can someone tell me what, oh, I guess I have a calculator here too, don't I? Minus 157.5. So I got 22.5 degrees. Okay, so theta, which is that same angle here. So my drawing's very small, but that angle and that angle are the same angle, right? So that's also theta. So now we can calculate that. Okay, first of all, that is this theta. The angle between that and that. Yep, that's that theta. And we can also calculate what FGG is, right? Because we only care about... Oh, no, never mind. FGG is already... No, we don't have to use that for that. It's already just mg. Yeah. So we know that angle there. So it's just the distance. So the distance is the total length divided by 2. 2.7 over 2 times the force of gravity, or the force of gravity on green, which is mg, right? Times sine of 22.5. Right? So 2.7 over 2 times the mass, which was 60, times 9.81 times sine of 22.5. Okay, so I will do that. 2.7 over 2 times 60 times 9.81 times sine of that. So sine of 22.5, 9.81, and 60. And math error. Why did I get math error? I missed the bracket probably. Yes. 304.08 Newton meters. This is again just going to be negative, right? It's going to be just stick a negative there because it's going in the negative torque direction, right? Torque is going that way. So my answer will just be the sum of these two, right? So my total torque is going to be negative 304.08 plus negative 2,207.25. So negative answer plus, well, I guess minus 2207.25. So negative 2,511.33. Yeah, it's close enough to the answer. Sig digs, I guess. No, not even sig digs, because they have, yeah, maybe sig digs. Yeah.
Isn't torque positive?
It doesn't have to be, right? It doesn't have to be. So since positive torque is that direction, that's positive torque. So both of these torques are trying to pull these guys down, right? Which would be it's trying to turn in that direction, right? Which is opposite, so negative.
But like, isn't it going? Because if you do the right-hand rule with the radius and the force, doesn't torque point up?
Well, let's see. So right-hand rule. So your fingers curl the way it's supposed to be turning, and we do.
Yeah. Oh wait, never mind.
No, you're okay.
Never mind.
Okay.
Yep. Sorry.
I think we got a room full of people going, what? What are we doing? So yeah. But yeah, okay, so we're good. Okay, let's see. Yeah, was someone gonna say something?
Yeah, was it? Could you go over like the angle part? Because I didn't understand.
Yeah, well, so I was just trying to find this little angle in here, that little angle, right? Because that's the same as our angle, our theta. Because if you just look at, like, if you have a line like that, that's our force, or that's our clock hand. There's a force acting like that, and we're just creating an imaginary line like that. Well, these angles will both be theta if they're parallel. Which they are parallel, right? Because the force is going straight down, and that's just an imaginary line we made going straight down. So that's like the center of the clock. Imagine that's the center of the clock. So you see, there's the center of our clock. We want to figure out what that little angle is. So we took the whole 180, right? Whole 180, and subtracted how far that clock hand has gone, right? So it's gone 30 plus 30 plus 30 plus 30 plus 30 plus a quarter of 30, because we're a quarter of the way through the hour. Okay. We'll do it again for the next one too. There's another part of the question, right? So I did 3. Let's do 820, and maybe we won't do 445 because it's also like a nice angle. So let's just do 820. Okay. Oh, I guess never mind. That's not a nice angle. Same as the last one, but yeah. Let's try 820. So this is going to be. Just start from here. Oops, a little smaller. So 820 is going to be, if that's 9 o'clock. So 820 the hour. I always forget which one's the hour hand and minute hand. So hour hand is the green one. So 820 is going to be a little bit past 8, and 20 is going to be, if this is. Wait, hold on. Do I want two lines? I missed the line. There. So this is going to be.
I don't understand why you subtract the previous torque on the.
They're both negative.
Oh, okay.
Right? They're both negative.
Okay, sorry.
No, don't worry. Yeah, you're good. So, okay, so similar problem now, right? So pretty much same. We just got to figure out all these angles, right? So let's start with the red one. So what's the torque done by the red one? Oh, you know what? I'm going to get... Well, maybe I still have it copied. Yes, I do. Good. So torque done by the red one. So torque done... right in the center of it, we have our force of gravity on the red one. And right in the center of this guy, we have the force of gravity on the green guy. So the torque caused by the force of gravity on the red one is its distance from the axis times the force of gravity on the red one times sine of theta, right? So again, if I create an imaginary line here, this theta is the same as this theta. So that's why it's useful to find that, right? So let's find that theta first, because we know everything else. We know R, we know FGR. FGR is just mg, right? So that theta is going to be 180 minus 60. 180 minus 30 minus 30. Right? So 180 minus 60 is 120. So I can just start plugging in. This is going to be, well, for the sake of just writing it, because I keep thinking I'm going to write it like this. This is just going to be mg times sine of theta. Okay, good. So now r is going to be this radius divided by 2. So 4.5 over 2 times m, which is 100 kilograms, times 9.81 times sine of 120. Right? And I can just plug that all in. So 4.5 times 4.5 divided by 2 times 100 times 9.81 times sine of 120. So I get 1,911.5 Newton meters, and we look, well, it's trying to push the minute hand this way, which is negative torque, so this should be negative. Okay. Let's try it for the green hand. So the torque done by the force of gravity on the green hand is the distance from the axis times the force of gravity on the green hand times sine of that angle. Okay, so we're looking for this angle there, yeah, which is going to be 180. Well, it's just going to be the angle of the clock, the angle that the clock is at this point, right? So from counting from here, or no, it's going to be 100. That angle minus 180. Yeah. So that angle, take away 180. That's going to be, so this whole angle that it's traversed minus 180. So you cut it off there. So you just have this angle, right? And that's the angle between the force, which is going straight down, and the radial vector, right? So, well, what's it at now? So it's at 180, okay, 210, 240. So it's going to be 240 plus, now one of these divots is 30. And how far past the hour? What fraction of the hour are we past? Well, we're 1/5 of the way, right? Or we're, what was it? We're at 20. No, not 1/5 of the way. We're at 20 over 60. Yeah, so 1/3 of the way. Yeah, sorry, I was thinking of 100. So we're 1/3 of the way, right? So this is just going to be 250 degrees. So that whole thing is 250. So theta, I'll write it over here. Theta equals 180. That angle, which was 250, minus 180 degrees, right? Which is just 70 degrees. Okay, so we have everything we need to know now. The radial vector, again, I'll just write it. So r equals mg sine theta. So r is half of that length, so 2.7 over 2 times the mass is 60, right? Times 9.81 times sine of 70 degrees. Okay, and so this is going to be 2.7 over 2 times 60 times 9.81 times sine of 70.
Why do you sine 70?
Y sine of 70? Is that what you asked?
Yeah.
Okay. 1 second. So 67 Newton meters. And one quick thing before I answer that is notice this is positive this time, right? Because the torque is trying to move the hand this way, right? That is positive torque. So it's a positive torque at the end. Okay. How did I get the angle 70? Well, what we're really looking for is that angle in there, which is theta. Okay? That angle in there. It's the distance, is the angle which is the same as this angle over here. The angle between the radial arm, right? The hand of the hour hand of the clock and the vertical line going straight down. Because the force of gravity goes straight down. So what we can do is to find that angle. That angle is going to be the whole angle that the clock hand has traversed, right, all the way to here, right, but minus 180. Take this away. Take this 180 away, half the circle. That angle that's left is going to be theta, right, because it's going to be the distance between there and there, that angle, right?
Why did you add 30 over 3? It's at 8 o'clock, right? So it should be 240 minus 180, right? Because it's at 8 o'clock. It's 8:20, right?
It's 8:20, yeah.
Mm-hmm.
So this would be because I'm a little past 8. I'm a little past 8, right? So it's going to be right. So it's going to be 120. That's 180. What am I talking about? 180. 210. 240, and I'm a little past that. In fact, I'm 30 over 3 past that. I'm a third of the way to the next hour. So I'm 30 degrees over 3. Because to the next hour would be 30 degrees. And we're a third of the way through the hour. So it's 30 over 3.
So it won't be right at 8, even though it says 8:20.
No, because the clock, the hour hand moves a little as it moves continuously, right? It doesn't just jump from hour to hour, right?
Okay, makes sense.
So,
sorry.
Yeah, go ahead.
Can you explain why it's sine theta again?
Why? What is, sorry?
Why do we take the sine of the angle?
Well, that's just part of the formula. That's just part of the formula for torque. Taking the sine of the angle.
Okay.
That's just part of the formula. So the formula for torque, right, is if I'm calculating torque, I need to find the distance from the axis that you're spinning around, that distance, times the magnitude of the force that's causing the torque, times the sine of the angle between those two things, between these two things.
Oh, okay.
Okay, that's the formula.
Wait, I still don't get how you got the angle. It doesn't make sense to me.
Well, does it make sense that we're looking for this angle here, this angle in there, right? This small one.
Yeah.
Right. That's because that's the angle between the force and that, right? So what would it be if we were at 9 o'clock exactly? What would that angle be?
Yeah, that's what I'm confused about. Would you measure it from 12 o'clock?
Yeah, you'd measure it from 12 o'clock, right? Well, it's just something we're doing. You don't that's just something we're doing to help answer the question, right? You measure it from 12 o'clock. This is 270. It's gone. Yeah. It's the amount of the amount of distance that it's traveled is 270 degrees, right? But it's not exactly 270. It's a little bit less than that, right? So we did a little bit differently. So instead of saying it went 270, right? We went it went to 8 o'clock, right? Which is 240, right? So it traveled 240 degrees, and a little bit more than that though. It's not exactly there, right? So since we're a third of the way through the hour, right? Then it's gone a third of the way to the next hour. So the distance to the next hour is 30 degrees. And so a third of that is 30 over 3. Since 20 minutes is a third of the way to the next hour.
Okay. Yeah, I see. Thank you.
Makes sense? No
For
problem.
the red one, how is it 120?
Degrees? Well,
yeah.
Just from here. So what I did is I said, okay, well, it's 30, 60, 90, 120. Measuring from here.
What? I thought you were trying to find the angle in between.
Oh, you're right. Yeah. Hold on. What did I do? Yeah, this angle is not that. Yeah, you're right. So this angle is going to be 108. So that angle is going to be the same as that angle. Yeah, you're right. For I didn't do that here. So it's going to be 180 minus that angle. Yeah, that's what it's going to be. So it's going to be 180, which is all the way to here, but take away that angle. All that's left is this arc length here, which is the angle of that is the angle we want. Right?
It's just 60, right?
It's 60, but you get the same thing if you do sine 120 or sine 60.
Oh, okay, yeah.
That's why it worked.
Yeah. Okay, there you go. So, and is it the right answer? Is that the like that's the correct thing? So I'll say answer minus 1911.5 negative. Yes, I got the right answer. Slightly different. I don't know why. Somewhere I'm rounding, I guess, or no, they're doing sig digs. That's what it is. Okay, should I do the last one or should we move on? It's completely up to whatever people say. Should I do 9:45?
It's fine.
Move on.
I think move on, but yeah.
We can move on.
So
I have a question.
Yeah, for sure.
Yeah. So I have two actually. So could you like scroll down a little bit
to here?
To like where you found like the torque like at the end. So yeah, how come it's like positive instead of like negative?
Because you see here, which way would the force of gravity is pulling it down. So which way would that hour hand move? Which way is it trying to force it to move, right? So it's trying to force it to move like this, right? And that is the positive torque direction. Counterclockwise is the positive torque direction.
Okay. And 30/3. But you get, I get like the 30 part, but like I don't get the 1/3 part. Is it because of like the?
How far into the next hour are we? If I'm 20 minutes out of the 60 minutes to get to the next hour, that's the same as 1/3 of the way to the next hour.
Oh, okay.
Does that make sense?
Yeah, that makes sense.
Yeah. Good. So yeah. Okay, so chapter 11. Chapter 11. So this is angular momentum. I hope I have it all here. Yeah, I have a few formulas for it. And I assume that also means, we're going to do conservation of angular momentum. Okay. Let's take a look. See how it goes. So, let me just have to sip my water. Oh, we might take a break. Yeah, how about let's take a 10-minute break before we keep going. Okay, let's take a 10-minute break, and then we'll start angular momentum right after. Okay, so yes, let's do that. Here, I'll move this back. Okay, so AFK stream, there you go. And I will be not back at noon, but I will be back at
after the test.
Yeah, after the test. Not quite. 47. Okay, so see you guys soon.
Was anyone else shook by the fact you couldn't go back on the CNE? CEN exam?
No, they said it.
Yeah.
Oh, they told us?
Yeah, what's on the slides?
Oh man, I didn't see that.
Bro, did you do this pledge thingy?
Yeah, I did the pledge thing. Yeah,
Oh, okay.
Yeah.
Because it had slides with it, so like the slides explained it, so it's on the slides.
Wait, for the previous question, does anybody get how he got the angle 70 degrees?
Yeah.
Yeah,
So
like sorry, 1 sec. I know how he got 250, but then I don't know what he did after.
Because it's actually past 10, even though it says 820, so it's like 1/3 of the way to 9. So you just add 30/3.
Yeah, so if you're calculating from 12 o'clock,
Okay,
then
yeah.
you have at 8:20 or whatever we calculate 8:20 we have 250 degrees, right?
250, yeah. I mean, slightly after 8, yeah, 250. And you just subtract 180 to find the angle in between.
180?
Because you're trying to find the angle in between that force vector and that FGG.
Oh, I see. Okay, okay, okay. That
Yeah.
makes sense. Okay. I was like, what is happening? Okay, thanks.
Problem.
God, we need to go through the study hall questions. There's so many, and there's stuff from like the beginning of the semester. I don't even remember them.
I'm here. Let me get this going again. Okay, there we go. Hi everybody. Can someone say something? Make sure I can hear them. And then
Yo.
Okay. Good.
Hello.
We're good. We're good. So we are about to start chapter 7. I also got a hot chocolate again, so that's good. I'm living a good life. And we're good, but not chapter 7, chapter 11. And so angular momentum is here, and we start with question 1 from angular momentum. So that's here, and then go back. Question 1. There we go. And it's just a cross product, so we could do that, sure. So, well, yeah, question 1 is just calculate the cross product between these two vectors. So we can do that. We've done linear algebra. So it would just be... do people want me to do the way with the determinants? Because I can, but we also know other ways to calculate cross products. You could just do that otherwise. You don't have to do the determinant way, I'm pretty sure. Do people want me to do that? Or no? Okay. I think I'll just do the normal way then. So 2, -3, 1, 2, -3, 1, 4, 5, -2, 4, 5, -2. Okay, so determinant of that is 6 minus 5, -1 plus 4,
yeah.
10 plus 12. So that's that. So 1, 3, 10 plus 12 is 22. So it's 1 I hat plus 3 j hat plus 22 k hat. And yes, there you go. So, okay, is everybody good with that? Just calculate cross product. That was a quick one. Let's do number 3. If A cross B equals A dot B, what is the angle between A and B? So that's not too hard to find. So if A cross B is equal to the magnitude of A times the magnitude of B times sine theta, right? And A dot B is equal to the magnitude of A times the magnitude of B cos theta. And we're asking for what theta are these the same? Well, we're pretty much just asking when is sine theta equal to cos theta. In other words, if I divide both sides by cos here. In other words, when is tan theta equal to 1? And that's theta equals pi over 4. Pi over 4. Is there many solutions to that? I don't know if there's multiple solutions to that. Tan equals... I don't know. I'll just say pi over 4. That's when they're equal.
Pi over 4 plus k.
That's true, but I think if it's past the circle, you would just count it as... You would just count it as, like... Yeah, that's true. That's true. Yeah. Plus 2 pi k. Or is it pi k? Is it just pi k?
It's pi k. For 10 is pi k.
Yep. Oh, okay. Because it's the period is pi? Is the period pi? I have my post thing here.
Yeah, it should be plus pi k.
Yeah.
Because its period is pi. Sine and cosine is 2 pi.
Yeah. Okay. So yeah, so there you go. So that's the answer to that. That's number 3. So number 8 is here. So number 8 is here. Okay. Non-isolated system angular momentum. So a particle moves in the xy plane with the velocity of that. Determine the angular momentum of the particle about the origin when its position vector is that. So 1.5. So the mass of the particle m equals 1.5 kilograms.
I can't hear you for some reason.
I think that might just. Can anyone else hear me?
Yeah, we can hear you.
Okay, so I think see if someone could tell her if she can't hear me. Someone tell her that it might be her. Okay, I think we're good. So determine the angular momentum of the particle about the origin when its position vector is that. So its velocity equals 4.2 I hat minus 3.6 J hat. its position vector is 1.5 I hat plus 2.2 j hat. And so the angular momentum is this. So the angular momentum is the inertia times the centripetal, the angular momentum. That's what the angular velocity. That's what the angular momentum is equal to, right? Since this is a point mass, we can say the inertia is. So we're calculating this. Right? We're calculating that. So since it's a point mass, we can just say the inertia is mr squared, right? Distance from the origin, because we're saying the inertia around the origin. Sorry, I can't say the right word. The angular momentum around the origin. And then the omega, well, remember we can relate linear and the angular quantities by just the factor of r, right? So it's just going to be v, the magnitude of v equals r omega, r magnitude of omega, I guess. Does that make sense? Okay, I think that makes sense. I think I'm going to leave the vector off of that one, although I don't think that's right. But anyways, that's what I've been doing so far. So we can break this up into x and y too, right? So m, w, although do we have to? I don't think we actually have to, do we? Because this would be just the magnitude. Well, okay, let's break it up into x, y, and let's just do that. Okay, so this is just for x. So the angular momentum in the x direction is just going to be the x position, and the x, and the x, and the radius is radius. Oh, radius is just the radius. So radius is just the magnitude of the r vector, right? But here, this is going to be the x component of that. Yeah. Okay. So mass is 1.5 times the magnitude of the position vector. So the magnitude of the position vector is 1.5 square root of 1.5 squared plus 2.2. Mm-hmm.
Okay, you hear me? Okay.
Yeah, I hear you.
But why the angular momentum you put x? I don't think angular momentum has a vector.
Yeah, I might be wrong about that. Although it looks like it should be. I wrote it as a vector here in the notes. Let me look at my notes here quickly. Because then... Yeah, I think you might be right. Let's see. Second for rotation. That's not what we need. We need angular. No, I don't need that. There, angular momentum. Yeah, you're right.
I just wanted to ask, can you also like multiply the mass by the velocity and then cross product that with the r?
Mass with the velocity. I know what you mean. I don't know what you. I know what you mean. I don't know if that would work though. Yeah.
Because mv would be the linear momentum, and the linear momentum cross product with r would give you angular momentum, right?
Yeah. Well, let's see here. I want to see that in writing here. Yeah, it looks like that should be right.
Because I just want to know if it works, because that was the first thing that I thought of, not what you do right now, which kind of makes me.
Well, I'm looking at this, and just from the notes from Springer's lecture, and the only times that the quantities are actually I ever see them related is f is s, the position equals r theta, the magnitude of v equals r magnitude of omega, and the tangential acceleration equals the r times the magnitude of the like rotation angular acceleration. So it doesn't say that about I here though, or it doesn't say that about what's it called, the L. right? L, I mean, it doesn't say it. I don't know if that's true or not, but R times P, right? It doesn't.
Oh, he doesn't mention the R cross product to P. Oh,
I don't see it.
I'm pretty sure Jesse did those.
I don't see it written.
I
Yeah,
have it here on my phone.
Although I feel like I remember him saying all the linear quantities can be just related by R, but
Oh, you're talking about the R cross P thing for linear momentum? I'm pretty sure that's in the next slide, the vector nature of rotation slide.
Oh,
okay. Then never mind. Just carry on.
11.2.
I just wanted to make sure that if that would actually work and if that was correct.
Yeah, the formula's in thing though. The next slide with R cross. Oh, it's R cross F, and there's some other ones also.
that's for torque, and then if I want to see the other ones too. Yeah, here. Yep, here it is. So there's a formula here. L equals R cross P. Yes, it is there. So yes. Okay. So the centripetal. I keep saying centripetal for the circle. I mean the angular momentum is equal to the radius, the radial vector, times the linear momentum. So, well, we can get the linear momentum just by multiplying every term in here by, just by multiplying every term in here by 1.5, right? So this will equal, the radial vector is 1.5, 2.2. 1.5, 2.2. I'm going to write it like a linear algebra thing. I'm crossing that with, multiply each thing in here by 1.5. So 1.5 times 1.5 times the velocity, 4.2 negative 3.6. 3.6, right? So this is 1.5. So this I kind of skipped a step there. I shouldn't have really. The linear momentum is the mass times the linear velocity. So we know that for each of the components, it's just going to be multiplied by 1.5. Right, so I can break this up in x and y, but it's just the same thing. It's just multiplying both terms by 1.5. So it's 2.2, because the mass is 1.5. Cross that with, so 1.5 times 4.2 is 6.3. And 1.5 times 3.6 is going to be negative 5.4. Okay, so, hold on. How do we cross it if it's, hold on. How do we cross it if it's, we just take the magnitude of each and then, I guess, or we just say it as a 0 at the end? Yeah, I guess we just say it as a 0 at the end. So 0, 0, and then we can do it? Yeah, that makes sense, actually. Right? Because cross product is an R3, really. It's an R3 thing, right? So it has to be like that. Yeah, that makes sense. So 1.5, 2.2, 0, 1.5, 2.2, 0, 6.3, negative 5.4, 0, 6.3, negative 5.4, 0. So this times this is 0. This times this is also 0. That doesn't look too good. 1.5 times negative 5.4 is negative 8.1 minus 2.2 times 6.3 is going to be 13.86. So negative 8.1 minus 13.86. So that's my answer, which doesn't quite seem right at all. 0, 0, negative 2.
Why don't you try it with the determinant way, like the IJ, and then like.
Wait, why wouldn't this be right?
It is right.
Isn't it
right?
perpendicular?
Yeah, it should be perpendicular because we were on the XY
Yeah.
plane.
Oh, we were right on the XY plane. You're right. Yeah. We were right on the XY plane. That's right. Yeah, that makes sense actually. Yeah. Do people want me to do it with the determinant thing? Because that's also a way I find it significantly more complicated than this.
You just do that.
Yeah, and could you just go over this method because I didn't catch it.
Yeah. This is just like from linear algebra. This is like how you do cross product. So it's just I just take this quickly. If I'm just trying to cross like 2, 5, 6 with 3, 1, 1. Let's just say I'm trying to cross these two. So you write each vector twice. So 2, 5, 6, 2, 5, 6, right? 3, 1, 1, 3, 1, 1. And then you cross out the first and last. And then you just find that, so our output is a 3-dimensional vector, right? So it'll have 3 components. And so the first component will be the determinant of that. That'll go here. The second component will be the determinant of that. That'll go there. And the third component will be the determinant of that. That'll go there.
Whoa, that's nuts.
It's actually exactly the same thing as what you do when you do the determinant thing with the IJK. It's just like a quicker way of getting to that. So it's really a trick of a trick, because the determinant thing with the IJK is already a trick. It's like a trick to find the cross product.
Lines actually confuse me.
Yeah, the lines are. I know the lines can be kind of confusing, but you try to think. Look where the 2 red ones are. That's the determinant there. The 2 green ones between that is the determinant. And
Just draw arrows, Adam. Maybe you'll understand if you draw.
It's just like, what if it's not a 3x1? You know.
The cross product is only defined in in R3. So if you want to do it in R2, you have to add a 0 to make it an R2.
Yeah.
So green. So the red is that. Green is that. And purple is that.
Yeah. Okay.
That determinant. Much faster way of doing determinant than doing a cross product than the other stuff.
Yeah. Okay. But is it 5 minus 6, or is it plus this time?
Well, just like you would find the determinant of a 2x2, right? So if you're finding A, B, C, D, the determinant of that is AD minus BC. AD minus BC.
Yeah. I just thought you said something about addition, so I was kind of confused. All right, that's cool.
Right, so that's how you do that. And so that's what I did here. I just did it with the zeros, right? And since we were in the XY plane, the cross product, the cross product is just going to be just the Z component. And is that the answer? Let's see. This was run number 8. Yeah, that is right. Okay. I just thought the number was going to be off, but no, that is right. I don't know why I assumed that. So yeah, so then that is L. They're equating it here. So that's the angular momentum.
So like actually go over what you just did, or just like quick step.
Well, so I just found this formula. In fact, I'm going to write this formula down. Let me write it down quickly here. L equals R cross linear momentum. So the angular momentum is equal to the cross product of the radial vector and the linear momentum. So radial vector, that's just the position from the origin. It gives us that. Position from the origin, right? 1.5, 2.2, 1.5, 2.2. I want to cross that with the linear momentum. Well, the linear momentum has 2 components. It has an x value, x component, and a y component, right? The px equals mvx, right? And py equals mvy. So in both of these cases, it's just you take the velocity and you multiply it by the mass. We know the mass gave us the mass. It was 1.5. We also know both velocities. So I just put that in a new vector, both of them multiplied by 1.5. Right, so the first component
Okay,
multiplied by 1.5.
No, sorry, go.
Well, go ahead. What was next? What was the next one?
No, I was saying, so what about I saw you have like AT equal R and alpha?
Something for me.
This is the same question, but I was doing a different way before. This is doing it a different way before. Yeah, that's all it was. Right. So, yeah, I would have gotten.
That's what it is wrong.
Well, I would not have gotten a very nice answer, because I would have gotten 0, 0 for both of those.
Okay.
And I don't know what I would do after that. Yeah. So
I need to eat something. I don't know.
I think you got your mic on again. Someone got their mic on again. But yeah, okay. So, okay, there's that. So then let's keep going. That was number 8. So let's look at number 9. Number 9 is this guy right here. So a particle of mass m moves in the xy plane with a velocity of that. Okay, so just in general, determine the angular momentum of the particle around the origin when it's positioned. So it's just the general case of what we just did, right? So the general case is that it's just going to be, right, so if I'm crossing pretty much so I said L was equal to the radial vector crossed with the momentum vector, right, linear momentum vector. Linear momentum vector is just m times vx, m times vy, right? So I'm just crossing this. So this is just going to be the radial vector, xy, crossed with m vx and m vy. Cross product is only defined in R3, so we got to put a 0 at the bottom here. And so now I just take the cross product. So it's going to be x, y, 0, x, y, 0. Okay. Then it's going to be m, vx, m, vy, 0, m, vx, m, vy, 0. Knock off the first and last ones. And I take determinant. So this determinant is 0, 0. So 0. Next determinant is also going to be 0. Right? And the last determinant is going to be x times mvy. So x times mvy minus y times mvx. And so the final answer is that the angular momentum of a particle like that is going to be x m vy minus y m vx k hat. So there's that. Okay. So just the general case. Okay, number 10. Number 10 is here. Number 10 is an actual question. Well, an actual word question. So, heading straight towards the summit of Pikes Peak, an airplane of mass that flies over the plains of Kansas at nearly a constant altitude with constant velocity of that. What is the plane's vector angular momentum relating to the wheat farmer on the ground directly below the airplane? Okay, not too bad to do. So, well, okay, ground, airplane, there, wow, okay, airplane, person, right? So we're looking for the angular momentum relating to this, right? So just say there's our middle. We said angular momentum was equal to the radial vector crossed with the momentum vector, the linear momentum vector, right? So, well, what's the radial vector? Well, the radial vector is, do we know anything about the radial vector? What's the relating to the directly below the airplane, right? So the person standing right there. Okay, well, what's the x component of that radial vector? X component is 0, right? What's the y component? Well, it's just the height of the plane. Well, the height of the plane is 4.3 kilometers. So I'll say 4,300 meters and 0 in the z direction, right? So we're going to cross that with momentum. Now remember, our momentum vector is just going to be the mass times the velocity in the x direction, the mass times the velocity in the y direction. So the mass is 1,200. 1,200. Velocity in the x direction, so moving left and right, that's 175. And then here is going to be the mass times the velocity in the y direction. Well, it says it has a constant altitude. So that's 0. Maybe I'll do it in red. But yeah. Right? So that's just equal to whatever that is. 1,200 times 175, 0. And again, you have to be defined in R3 to do a cross product. So yeah. That's not technically equal. That's equal up there. Okay, so let's take this cross product. So it's just going to be 0, 4, 3, 0, 0, 0. Honestly, yeah, hold on. No, there's a better way to do this. Another way to calculate a cross product is to just do, if I want to do R, since there's only one component in both of these, a little faster to just do this. We just need the, oh no, we don't need the magnitude. No, we need the direction too. Never mind. So, what's going to be 0? For the dot product, it would be 0. Dot product would be 0. Yeah,
sorry.
Don't worry. 4, 3, 0, 0, 0, 0, 4, 3, 0, 0, 0. I'll do that multiplication. So 1,200 times 175 is 210,000, 0, 0, 210,000, 0, 0. Cross out the first and last rows or columns, and let's put it together. So this times this, 0. So sorry, this times this minus this times this, 0. This times this, 0 minus this times this, 0 is 0. Okay, and finally, this times this is 0 minus this. That's actually a number there, right? So another 0 here. So it's just going to be negative 4,300 times 210,000. Right? So that's just going to be answer times 4,300. And I get 0.03 times 10 to the 7. And there. Oh, 10 to the 9? 6. Should be 8. 6.
I never heard of this method.
7, 8. It should be
It's
8.
8. It's
But-
8 and it's just negative as well.
Yeah, it's negative 2. I forgot about that. But the answer actually says 10 to the 9
Yeah.
in the book. Did I miss a 0 or? Let's see.
No, it's 8.
Yeah,
I don't
looks like
know.
maybe it's a mistake. Let's say 2, 1, 2, 3.
Negative 9.03 times 10 to the 9th as well.
You got 9? You got 10 to the 9?
Yeah.
How? What did you do differently than me?
Uh,
The mass is 12,000, not 1,200 kilograms.
Yes. Yep. There you go. Missed a 0 there. So I missed a 0. Well, here. So I missed a 0. Well, this would be one more 0. So this would be one more 0. So this would be a 9. There you go. Okay. And so that was A. Part B, does this value change as the airplane continues its motion along a straight line? Well, its momentum is the same. But in relation to the thing, well, yeah. Well, sorry, so the momentum actually... Yeah, it would change because this value doesn't change, but the radial value does change, right? So your x component would start to increase. You'd have a positive x component there, which means you'd start having a value in this position, right? In that position right there, right? Which means this second value is going to start to go down because it'll be minus that, which is not quite the answer. It's going to be, oh wait, no. But the answer also says no. Does this value change? And it says no. Why would it change? This would have a x component now. Would P be the same? Yep, P would be the same.
Why are you saying that the radius, sorry, not radius, the R vector is gonna increase again? Why did you say that?
Well, because if the plane starts moving forward, right? If the plane starts moving forward,
Yeah.
right? Whatever, there's the plane. Then this now has an x component.
All right.
Right.
Well, wouldn't when you're finding the determinant, wouldn't that be multiplied by 0 and then just cancel out?
Oh, you're right. Yes, you're right.
Yeah.
Yes, that's
Okay.
true. Multiply by 0 here. There you go. That's it.
Sorry, can you repeat that? What he said?
What I was saying was right technically about like, okay, this would have an x component, right? So then we'd get a number here, but it doesn't matter. It's still being multiplied by 0 to find the determinant there, to find this component. So this component would not go up still.
Okay.
It would still be 0. This would still be 0. So yeah. So the angular momentum would not change. Yeah. Which makes sense because conservation laws and everything. Yeah. Well, actually, I'll leave that plain there, I guess. But yeah. Okay, so there's that question. Oh, no, we're not done yet. What is the angular momentum relative to the summit of the peak? An airplane of mass, that's working at this. Well, we don't know. Okay, so assuming that assuming that this is the airplane. Okay, draw my beautiful airplane again. There. Wow. Okay. Okay. Whatever. That's
art.
Yeah, that did not work. Okay. Here. There. A little better. Looks like a fish now, but that's okay. There. Okay. So there's the airplane. It's assuming it's headed directly to. Still on a mountain. Directly towards the peak of a mountain. Right there. So the radial vector like this is just an x component. Let's call that x component L. Okay. So well, I can't call it L. Actually, let's just call it x. So then the angular momentum is going to be the radial vector, which is just x 0 0, crossed with the same momentum vector, the same linear momentum, which is the same here, which is just going to be that. So 1 2 0 0 0 12,000, yeah, times 175 times that. So this is just going to be x 0 0 x 0 0. This was 210. No, this was more than that. It was 2,100,000. I think, right? Wasn't it? Yeah. So I knock off this. Yeah. 0 0. 2,100,000. 0 0. Knock that off. So all that matters is this. So that's 0. That's also 0. That's also 0. That's there. It's all 0. So 0. I guess maybe I could have figured that out. Yes, I could have figured that out before too, actually, because it's not moving in a circle. So, but at least we can see it. But the angular momentum would be 0 0 0, because for it, like, you have to be going around the radius of a circle to have angular momentum, because it has an angle has to be changing to have angular momentum, right? But this angle, the angle between the radial vector and its path, is always 0. So it would have 0 angular momentum. But anyways, we showed it here too, by actually trying to take the cross product, and we got 0 0 0. So yeah. Okay. So let's go to 15, unless anyone has any questions. Let's go to 15. So let me open that up here. Okay. A ball having a mass m is fastened at the end of a flagpole that is connected to the side of a tall building at a point P as shown in that figure. The length of the flagpole is L, and it makes an angle of theta with the x-axis. The ball becomes loose and starts to fall with that acceleration. Determine the angular momentum of the ball about point P, okay, as a function of time. Okay. So, well, yeah, okay, what would the angular momentum? So angular momentum is, again, let's just do equal to the radial vector. Well, what would the radial vector be? This radial vector doesn't change, so we might have to do it in components. So, yeah. Oh, no. That doesn't make sense. Hold on. So angle between that and... Okay, let's stick with this. Do we know the mass? Yeah, we know mass and the velocity. Yeah, well, we know the acceleration at least. And the velocity. Initial velocity is 0 times t. Okay, so r cross p is we're looking for the angular momentum. The radial vector is this length. It will be what do we know? Mass is m. Oh, there's a point P. Length L. Theta with the x-axis. Well, what
I
angle
think we
would...
may have to use the other formula.
Yeah, I'm thinking
It
too.
might
I'm
be
thinking that too. Yeah, but what formula?
I omega.
Yeah.
L equals omega.
So the angular momentum equals the inertia
Moment.
times W. So it's a point mass, so mr squared times omega. What's its speed at time t? Speed as a function of time. Well, we know its initial angular momentum is 0. We know its we know its tangential. Well, do we know its tangential acceleration? Yeah, I think we do. Tangential acceleration is negative g. Right. Well, okay, I guess I'll say j hat. And then, so I can convert that by a factor of r, where r is L. That doesn't make sense because L will not always be the radius as it's falling.
Can't use that because it's not angular. Well, it's not angular moment, right?
L?
Like you can't convert AT to acceleration. I think. I'm not sure.
Well, I think I can because this isn't alpha, but I can say it would be r times it would be negative g over r j hat would be angular because at equals r alpha.
Oh, sweet dog.
But r is not one of the variables we know, and it's not L because it's L to begin with, but that's not true here. That length is not L.
There's another equation, mvr sine theta.
mvr sine theta?
Yeah.
So L is equal to mvr sine theta, like that? Mass times the linear velocity.
Velocity and magnitude of r.
PR is linear momentum, non-angular.
Yeah, but I think it might be okay because we're still doing a factor of r. But still, I don't know what... okay, I guess maybe we can find that. Sine
I
theta.
still don't understand why there is an angular momentum in play because if fall down, there is no
Well, you can still even if there's not like a rotation, there still can be. You can still think of like an angular thing happening. So because you're moving around point P, the angle that's created here, right? This angle is different than this angle, right? This angle is less, right? That phi. So the angle is changing. So there is some sort of angular velocity. There's some sort of angular stuff happening here, right? Because if you make a reference, say like, okay, well,
in that sense, okay.
Right? So yeah, it's not rotating, you're right, but there still is some sort of angular stuff going on, right? So yeah.
I think we can convert AT to alpha and use that to find omega.
So like this.
Yeah. Somehow.
Do we need omega? But if this is the formula,
I think you just make a radius a
You just make what? Sorry.
radius a function of time.
Yeah, yeah. So what would that be as a function of time? That would be this distance. Oh, that would be.
Maybe do you do the conservatives of angular momentum? In the beginning, the piece is together with the pole. There is that kind of mass, and that kind of.
Yeah. So.
And then there is the change of angular momentum on the second part that is only the ball, but the other part is always still zero. So that is the.
But.
We still don't know omega.
Still don't know omega.
So in this case, you know when you put R, right? It's L, right?
Here, this R. Yeah, this here. Okay, nothing else. I can't hear you if you're talking. If someone said something there.
Somebody post a solution.
Okay, let's see.
Well, it's a link to a solution.
In homework help? Or no? In discussion?
No discussions. Yeah.
Okay. Let's take a look. So, a ball having mass m, length L, flagpole, acceleration that. To determine the angular momentum. What? I don't know what that's simple. A, G. I don't know. The ball about P. What they call it Q for some reason. I don't know. Determine the angular momentum. The ball about P as a function of time. Yeah, that makes sense. So take these as components. Inertial position of the ball, R naught equals L cos. The formula calculating position. Initial velocity equals. Therefore, is that alpha? No. Is that alpha? I think that's alpha. No, it's L. No, wait, what is that? No, that's R. That's an R. Okay. R. L cos theta.
See what they did. No.
So the final thing is, momentum is mg. Determinant of that. So, first of all, get the position R as a function of theta. Really. So we say if we have a flagpole like this, right? Then and we know that's L, right? Then this is going to be L cos theta, and this is going to be L sine theta. So R as a function of theta, really, I won't write it like that, is going to be L sine theta. Well, but hold on. That's not true, because then that's not going to be here. It's not L anymore.
There's also another solution. If you want to look at that.
Yeah, I see.
It's the same thing though.
Oh, it's too blurry. Is that any better or no? Well, I can't really hear an original. That's better. Okay. So connected to the link point P, the length. Ball about point P neglect with air resistance. Okay. Yes. Recall that angular momentum is given by R times P. P equals mv. And since gravity is the only force acting on the ball, V equals. That's from. Oh no, that's just the velocity. Yeah. V equals. What is that? V equals.
It makes sense because we had to break the position vector into x and y components, and that's what they did.
Oh, and then R is L cos theta. L equals sine theta minus 1/2 GT. What is that saying there? V sub G J hat? V sub J hat?
Static equation.
But this right here. This.
I think that's V final.
V equals, but it should be just negative GT. Oh, okay. So this is just yeah. This is just that, but I don't really know what that's writing there. This and geometry R. My problem is that, sure, here R. At the initial condition, R is, if this is L, and this is theta, then this is L cos theta, and this is L sine theta. But not at any time after. It's not L anymore.
Over time, like the L changes. Like if you put you know how you imagine like a circle, right? And then as you like create that path, L is gonna like L cos theta gets a little bit bigger, and then like L sine theta like gets smaller.
Well, L cos theta would get the same, wouldn't it? This would stay the same, this quantity. This would get smaller.
Like, because cos theta, as theta goes to 0, it becomes cos 1, which will equal L.
But that doesn't even.
But with the rod, it's just falling.
Yeah, yeah. So that here, this radius will not be L anymore. That'll just be R. It won't be L. It will have nothing to do with L. This distance will still be L cos theta, right? But this will just
change it. Yeah.
That radius will be R now. So this will be R sine theta. That this distance will be R sine theta. This distance is L sine theta.
I don't know what this solution is saying, but the other solution is pretty clear.
Yeah. Okay. Well, let me
I'm not sure what's going on here.
I think the L sine theta
R sine theta versus L sine. Is L from like this point at the top to like the
L is
bottom?
like the rod. They give you the length of the rod, right? That's like the length of the rod here.
So are you saying that if it was fully upwards, you have L sine? I'm confused with the L sine theta right here.
This L sine theta? Well, yeah. At the initial condition where t equals 0, right? It hasn't fallen yet. Yeah, its height above point P. This is point P. Would be L sine theta to get the y component. Would be L sine theta. Right. But any time after, L is not that radius is not L anymore. It's just some other number. Some other number R.
Changing because of gravity, because gravity is only in the y direction.
Mm-hmm.
So they use the kinematic equation, like RF equals RI.
So it would be L. It would be L sine theta minus something minus
G divided by.
It's kind of like those rates questions in math. That's what came to my mind first.
Yeah. Okay. So yeah. Let's figure out how much it's falling as a function of time. Yeah. Okay. So
yeah.
Where did this send me? View. Oh boy, we're sideways now somehow. Somehow I'm writing in the middle of the screen. Okay. I don't know what happened, but all right. So where did the question go? Didn't I copy and paste the question here somewhere?
Black poll question. The flag one.
Oh, it's the flag. Okay,
you
yeah,
gonna
that's
bring that
true.
over?
I just forgot that it was a flag.
You gonna bring it over? Yeah.
There. Okay, we're good.
Oh.
So, well, not really good, actually, are we? So let's just move this. Move it down. Come on. I'll move it down here. Okay. So, yeah, that makes sense. Okay, so the radial vector will always have a x component of L cos theta. That'll always be the x component. But the y component will be L sine theta minus the amount that it's fallen, delta y. So delta y, if we just use our normal kinematic equation, we can say delta y equals VIY t plus 1/2 AT squared. VIY is 0, right? So it's just 1/2 A is negative G T squared. So we're just delta y, so we're just adding delta y. So this is going to be minus 1/2 GT squared. Okay, so that's our radial vector. So we have that at least. Now our momentum vector is just going to be, our momentum vector is the mass, so the only velocity it has is, again, I can just find VF, right? So VF is just going to be VFY equals VIY plus AT. So 0. So just AT. Right? Okay. So VFY is just negative GT. So that's the final y velocity. Why did I need that? For momentum. So at time t, we cross this. So the x component will be 0, z component will be 0, z component will be 0. And it'll have a negative GT times m. So negative mgt momentum at any moment. So sorry, this is the L now. This is R and this is P. Okay. Should work. Is that what they did here? Looks like they just called it different letters, but yeah, it looks like it. Okay, so let's try it. Let me just copy this. So this will be, if I cross this, it's going to be L cos theta, L sine theta minus 1/2 GT squared, 0 L cos theta, L sine theta minus 1/2 GT squared, 0, 0, negative mgt, 0, 0, negative mgt, 0. So this times this times this is 0. This times this times this is 0. This times this is going to be negative L cos theta mgt times that is 0. So my final answer for that is it's going to be negative L mgt cos theta k hat. Yes. There you go. That's it.
Yo, what did you just write at the end? What's that?
What's what? This here?
No. Just the thing with the vector sign.
This here?
One more
That's just
down.
K hat. That's just
After T cos theta.
It's just a Z component K hat.
Oh, this thing here. It's just
Yeah.
K hat, like the unit vector. My K's are weird. I don't know how to draw K. So yeah, it's a K.
Yeah.
There.
Okay.
K hat.
Beautiful.
Yeah, that's it.
Could you scroll up just a little bit to the part? Yeah, it's up. Yeah, right there. Thank you.
Good. Weird question. Not the scroll up, the question itself. That's the weird question.
Yeah, you can move on now. I just have to copy that little vector thing.
Okay, well, there's more to it. There's more to it. So, for what physical reason does the angular momentum change? Well, angular momentum changes when there's some kind of torque being applied, and the torque that's being applied is the gravity. So, there you go. What is the rate of change of the angular momentum of the ball around point P? The rate of change of the angular momentum is... The rate of change of the angular momentum is the mass times the acceleration, isn't it? So that's just going to be... Right, so F equals ma is actually F equals dp by dt, right? So that's kind of what I'm looking at. So would it be the same? No, but would it be the same there? No. Rate of change, angular momentum.
Oh, wait, one sec.
So, just look at this for a second.
Would it simply be the derivative?
I guess so. Then I need a function for the angular derivative. Oh, well, I have a function. I have a function. I just take the derivative of that with respect to t. Yeah, I just take the
I think so.
I think I just take the derivative of that with respect to t. Yeah, you're right. So dl by dt would be it would just be, move the 1 down. That's a 0. So it would just be negative L mg cos theta. There. Right, the t goes... Yeah, that makes sense. Okay, is that the answer? I don't know. Let's see. For number 15, I don't have the answer. Maybe let's look in the book quickly. Let's actually look... window. Answers to quick quizzes. What was this, 15? For chapter... This?
Isn't it 11?
Yeah, it's 11. Chapter 11, number 15. I have mg. Yeah, that's right. Yeah, that's it. Just get rid of the t because take the derivative. There you go. That's right. Okay, so we did 15. Let's take a look. I mean, yeah.
Did you guys solve it? I was just getting kicked out like 3 times, so I didn't say the last part.
Oh yeah, okay. So, you didn't see the part D, or you didn't see the end of like the main part of the question?
Just the end part, I think.
So, well, the end part was just finding the derivative. It just asked us for the derivative of our angular momentum function with respect to time. So if L was negative that mgt, that's a t cos theta, right? Then derivative, take the derivative with respect to t. So t goes away.
What's the variable in this?
With respect to t, right? So that's the variable that we're
Okay.
What's in the numerator of the t?
dl like dx by
dl.
like dy by dt.
Yeah.
Wait, can you scroll up for a second? Because I didn't get m in my equation.
And this is how fast the ball is falling, right?
The angular momentum. So related to how fast the ball is falling. Yes.
It's on a pivot or something.
Well, no, it's so that's what it's like. It's not on a pivot. It's completely released from here, right? But you don't have to be rotating for there to be an angular velocity. Just an angle has to be changing, or an angular anything. So this angle is the angle that's changing, right? This theta here is changing.
Yeah.
So there is some sort of angular momentum, angular everything going on because that angle's changing.
Yeah, because it's constantly decreasing. Eh? Yeah.
Yeah.
Okay. Thanks.
Okay, and then someone said they didn't get their m in the final answer. Did you multiply your velocity vector by m? Because it's momentum. Momentum is m times v.
Oh no, I just did the cross product wrong. Okay, great.
Oh, okay. There you go.
down.
So yeah. Okay, that was a tough question, but we got through it. We figured it out. So
For the V, you just have G times T, just a while ago.
let's see. I wrote it up here a little bit better. For the velocity vector is 0, 0, because in the x and y direction, it's not moving this way. It's also not moving like towards us, right? So x and z. So x and z direction is 0, and then for y, I just used this formula. VFY equals VIY plus AT to solve for VFY.
Okay.
So,
yeah.
So that's what goes there. Negative GT, right? And so momentum is just that times mass.
Yeah.
Right. Okay. So that was 15. So 19 is next. Is there a picture on the next page here? Yes, there is. So 19 and the other half of 19. Looks like another Big Ben problem. So there's that. Okay. 1 second. Did you? Be back in just 1 second, guys. Sorry. Just let me. Muted the mic a little too fast there, didn't I? Back in just a second.
Yeah.
Okay, we're good. So, number 19. Big Ben, again with the picture. The Parliament Clock Tower in London has an hour and minute hand with those lengths and those masses. Calculate the total angular momentum of these hands about the center point. So long, thin, rotating rods about one end. Assume the hour and minute hands are rotating constant rate of 1 revolution per 12 hours and 60 minutes respectively. 12 hours and 60 minutes respectively. So the calculate total angular momentum of these, I guess the angular momentums put together. Okay. So again, the angular momentum of the, let's start with the hour hand, right, is going to be the radial vector of the hour hand times the momentum, times the linear momentum of the hour hand. We'll cross product with that. So the radial vector, well, it's just going to be the length of the radial vector. Hold on. Yeah. So if it has so 1 hour and minute is rotating it. The radial vector is different depending on what it is. Let me look at this. There's another formula someone set up here that we had. That was this. MVR sine theta. Because it's P. Well, yeah, that's just kind of. Yeah.
I omega 2.
What is this? Sorry, what is it?
I omega.
Oh, yeah.
The,
Maybe that'll be more helpful. So L is also equal to the inertia times omega. Inertia, well, they're thin rods rotate, so we can probably find the inertia of a rod. Is that what's rotating? Yeah, I guess we could probably find that. And then assume, so that's probably what we need to do actually. And then the angular velocity, yeah, we can figure that out. Okay, that won't be bad here. So we have to look in the table for the thing for that. I think someone pinned it in the chat.
1/3 mr squared.
1/3
Pretty
mr
sure
squared.
it was.
Yeah. Oh, okay. Let's just make sure and then. So. Oh, there's that formula sheet that I didn't take out of the printer.
Yeah, no, but
Is it?
I have it.
Here I have it now too. So rotating around the end is, well, it's too blurry for me to see. Long thin rod with rotation through end. It's definitely 1 over something mr squared.
It's one. I'm pretty sure it's 1/3. Maybe it's in my notes.
It looks like a 3. Yeah, it could be yeah, let's just go with 1/3. It looks like a 3. It's more of just a blob, but yeah, it looks like a 3. So 1/3.
Wait, what table are you looking at?
The one that Jasper sent. The one that I think Jasper sent, or yeah, the one that Jasper sent. Oh, sorry, but where'd the table come from? Well, it's from lecture notes. I'm sure I have it in one of these piles here.
Oh, so the rod is the rotation through the center, right? Not through the end.
Yeah, the axis of rotation. Well, the axis of rotation is gonna be the center, right? So.
Well, okay, because like when it says through the center, it says 1/12 ml squared.
Oh no, sorry. Yeah, it's through the it's through the end because look, is the rod rotating like this, right?
Oh, okay.
Or is it rotating
Like
just like that? It's not spinning around the center, it's spinning around the end.
Okay, I see. Okay, thank you.
So is it like the table of like centroid or something? Is it like that
Yeah,
that
it
we
has
use?
just those values there, right?
Okay, all right.
So 1/3 mr squared times.
Where is that? Like, is it supposed to be in the discussion chat or the other?
Yeah, I
chat?
don't know where it is. I couldn't see it.
I think it's discussions. That's where I found it. Discussion.
I didn't find it. I don't know where it is.
It's pinned. I'm pretty sure. Yeah, it's pinned in discussions.
Yeah. Jasper's notes are pinned in discussions. Jasper's what's it called? Formula sheet. You'll see it. It's not a big picture. It just says PDF version formula sheet PDF. That's all it says, and then you'll see it there. It's the third thing pinned in discussions.
Yeah, it's 1/3.
How do I see things that are pinned? Oh my god.
You go to discussions, and then on the top right corner, there's a little pin icon.
Oh, all right. Okay,
And the third thing there. Yeah. There you go.
All right. Thank you.
Good. No problem. So let's look at our hour hand, right? So what is the angular velocity of our hour hand? Well, the angular velocity is just the, one full revolution per 12 hours. So 1 full revolution is 2 pi radians per 12 hours, right? Just convert that to so hours to minutes. So in 1 hour there's 60 minutes, and from minutes to second, so in 1 minute there's 60 seconds. So then just 2 pi over 12 times 60 times 60. So I get an angular velocity of 1.45 times 10 to the, I can't read it because it's dark here, -4. Times 10 to the -4 radians per second, right? So that's our angular velocity. And so I just plug that in here. I know m, I know r, right? So this is 1/3. M we said was, for the hour hand, is 60. R is the length. Oh, wait. Yeah. R is the length of the whole thing. Yeah, of the whole thing. So it's just...
Yeah, it's the length of the rod.
Yeah, 2.7. I was thinking, because before we had to do 2.7 divided by 2, but that was for torque, because we were looking for center of mass. Here we don't need center of mass. We just need the length of the whole thing. Yeah. MR.
What about the other length, the 4.7 length?
So we'll do that. We'll do that for the other hand. We're doing each hand separately of the clock, right?
The 4.5.
Yeah, that we use that for the other hand of the clock.
Oh no, I can't hear you.
Oh.
Okay.
We can hear you. Well, she can't hear me, so she can't.
Can hear you, yeah.
So this is going to be so this I'll just plug this in. So it's going to be 20 times 2.7 squared times 1.45 times 10 to the negative 4. So I got 0.0211. That's L for the hour hand. I guess because it wants total, so we just add them together at the end. I don't know. Assume that. So let's do for the minute hand now. For the minute hand, L is equal to I times omega. Let's leave it like that. So again, 1/3 mr squared times the angular velocity. So this is the angular velocity for the hour hand. We want the angular velocity for the minute hand. So the angular velocity for the minute hand is going to be 2 pi every 60 minutes. Right? And I just want to convert that from minutes to seconds. So there's 60 seconds in 1 minute. So it's 2 pi over 60 times 60. Yeah. So I got omega m is 1.75 times 10 to the negative 3. And now I just plug that into this. So 1/3 m is 100, r 4.7 I think it was. I'll check that in a second. And this was 1.75 times 10 to the negative 3. And 4.5. 4.5. So 100 over 3 times squared times that is 4.5 times 1.75 times 10 to the negative 3. So I got my L for the minute hand to be 1.18 equals L for the minute hand. And so the total is just them together. So L total is 1.18. Oh wait, am I supposed to be doing this as a... Yeah, no, I think it's okay. I think I just add them together. If we don't get the right answer, it's 0.0211. So this is 0.02. So this would be a 2. So 1.2011, I think. Let me just make sure of that. 1.18 plus 0.0211. 1.2011. Yep, good. We don't have any units on any of this. So what would the units of that be? That would be let's see, what would that be? No, probably shouldn't be in this book. Does anybody know what the units are supposed to be on that? Angular momentum is this one. No, that's not angular momentum. That's angular momentum. And
kilograms meters squared per second.
Kilograms times meters squared per second.
Yeah, I don't know where the radians go though.
Radians aren't actually a unit, so they don't go anywhere. You just write them so it's not confusing, but radian is not a unit. It's you just yeah, that's why. So it's okay if things are off by a radian, because it's just like it's not actually like you don't count radians. The radian is like the way it's designed. It's a little different. But that's more about math. So Yeah, so there you go. Okay, so then that's and is that the answer? Let's see if that's the answer. Number 19. Okay, it's not right here, so I'll have to find it in here. 19, 1.2. 1.2. Okay, we're good. That is the answer.
Can you recap this question though?
Yeah.
Because like from the inertia omega thing. Well,
So,
whatever.
Ignore this. This was just me thinking about other stuff. So for this one, for the hour hand, well, for the clock, we have two hands. We have the hour hand and the minute hand. Each of those things have angular momentum, right? And so the question was just asking, calculate both angular momentums and then just add them up. So first angular momentum for the hour hand, we use this formula. Angular momentum equals I omega, right? The inertia times the angular velocity. So the inertia for a rod rotating around one of the ends is 1/3 mr squared. Okay, that's just from a table. The angular velocity of the hour hand, well, we calculated that here. It does 2 pi full revolutions per 12 hours. So that's an angular velocity, right? Theta per time. So I just converted that into radians per second and then plugged it all into this formula. I knew m and r from the question. R is just the radius, just the length of the pole, and m was 60.
Yeah.
And so I found the angular momentum of the hour hand like that, and then did the exact same thing for the minute hand. Just
simple question.
Yeah, it wasn't bad. It wasn't bad for sure.
Wait, was there like apart from the summer sheet, there was a next thing with the like inertias? 'Cause I don't think it's on the summer sheet that Jasper sent.
It is. You have to slow it down a bit.
Like yeah, just inertias like different calculations. Yeah.
Well, I have this is what I have for inertia. Inertia is I omega. Inertia is r crossed with p. And there is the other one, which is essentially just this, but as a product, as like an actual as a product. So it's
that's the angular momentum. I'm talking about I.
Oh, you want this? You wanted this is what you're asking about?
Yeah.
I? Oh, sorry.
It's okay. I think someone had it in the group this morning or something.
Yeah, I just have it from this sheet here.
Yeah. What was the third angular momentum?
The third one would have just been this as an actual product. So it would just be L equals R, the magnitude of R, times the magnitude of P, but the magnitude of P we know is just MV, right? Times sine theta.
Sine theta. Why are we cross producting again?
This and this are the same thing. Well, this is just one of the definitions of angular momentum.
Okay.
That's just one of the definitions, right?
That's cool.
Cool. Tomorrow's session, are we also going over? What are we going over again?
Well, we're gonna finish. We're gonna finish angular momentum, and most of it's gonna be. There's only 2 questions left for me, or 3 really, and then we'll do static equilibrium. We'll try to do all. We'll see how many we can finish of the static equilibrium problems. We'll probably get through all of them, and then hopefully, I mean, I'll do because it's the day of the test, so I'll probably do 4 hours tomorrow, starting at 10, and so we'll get everything done.
Yo.
Also,
starting at 10. That's to isn't the exam at 3?
It's at 3, yeah. So I'll be done 2. That's the late. So.
Is everyone okay with starting at 9 instead, or is that too early?
Well, we could. I don't mind. I don't mind. I might. Let me think of that. Yeah. Well, it's a little bit late to change it, but
you can pull it later or something. I don't know.
Can you just quickly go over it again for me?
This question?
I don't know what. Yeah, this entire
No.
because I don't
it's
know
just whether
why.
Or not. You can start the next question actually.
I think. Can you hear there's someone else talking too? I don't know if you can hear them talking. There's someone else talking.
Yeah. I can't hear you.
Yeah. That's what it is. Okay, go ahead. The person who was asking a question.
Yeah, I was saying, can you go over the entire question? Because I don't know why, but your voice disconnected. I could see that you were talking, but you weren't. I wasn't hearing you. Sorry.
So no problem at all. So the question wanted us to find 2 angular momentums and just add them together. one for each of one for the hour hand and one for the minute hand, right? So we use this formula for angular momentum. Angular momentum is equal to the inertia times the angular velocity. Right? The inertia is this, which just from the table we know from a pole spinning from its end, it's 1/3 mr squared. Right? Poles, bars spinning from
And
its
it's
end.
different for each thing.
For each shape, for each shape rotating. Yeah, this is for a pole, and it's also different for like if it was rotating around its center. Right?
Oh, okay.
It's also that's also different.
All right.
So then we took that from the table.
Rotating on the end or on the center point?
No, on the end, because like it's the hand of a clock, right? So it's rotating on the end.
Oh, yeah.
Right. Okay. And then we multiply it by omega, the angular speed of the hour hand. Yeah, the hour hand. And so I found that so it does 2 pi radians. It does a full rotation 2 pi in 12 hours. Mm-hmm. So I just converted that from radians per hour to radians per second, and then just used that for omega and plugged everything in, and I got that.
Okay, so you're basically giving all the information. Okay.
Yes, you
I was just gonna. Okay. Yeah. Okay. Okay. That was all right. Thank you.
Good. No problem. Okay. Well, that's all the questions I'll do for today. It's 9 o'clock, so we're done for today. But I'll stick around if anyone has any other questions just to finish up. But that's the last practice question we're gonna do tomorrow. Maybe I don't know what I'll do.
If you're gonna make the session earlier, like at 9 or something, can you put in the tutor announcements?
For sure. 100% I'll put in the tutor announcements.
Just in case, because if I wake up too early, I don't.
I know. Yeah. Oh, no, 100% it'll be in tutor announcements if I'm making it earlier. It's just thinking, should I? Yeah. Maybe I'll make a poll and see what people think. But I think I just will. And we'll see what's going on. Yeah. Because what's the difference? It's better to have time there.
All right. Thank you.
Okay.
You're literally the reason why I passed my linear algebra exam.
I'm happy.
So thank you.
Very good. No problem. I'm happy to.
All right.
Okay. Bye, everybody. Have a good night.
Good night. See you in the morning, man.
Yeah.
Bye.
See you tomorrow. Bye.